Okay. So these are the notes for section 3.4. Just making sure the volume is working correctly. I think it is, but just want to make sure. Okay. So, in this section, there's a variety of functions you should be aware of when you're that you should just have a basic understanding of when you're doing graphing or whatever it is you may do. But if you're doing any graphing techniques, or just to have a basic idea of graphing certain types of functions, there are a variety of functions we're going to look at here that you just need to be familiar with. There's just no way around it. And we're also going to look at piecewise functions, which is a specific kind of function, but we'll get to that when we see it. So it's very important that you see the basic structures of most types of functions that you'll see in mathematics. And having a basic idea of what they look like is important going forward, because that'll help you to remember what certain graphs look like and any variations of those graphs will stem from the basic variety of specific functions. So just as a warm-up exercise, we're going to look at graphing the function, the cube root of x. Okay? So if we're going to look at that, the way we can get a variety of these get a structure of these graphs is by looking at symmetry. So determine whether the function, the cube root of x, is even, odd, or neither. So we know how to look at whether a function is even or not, right? We do this, right? F at x equals f at negative x. So that's how we check to see if something is even. So if this is true for this function, then it's even. So let's try it. So we already know what the function is equal to. It's equal to the cube root of x. Okay. But what is the function at negative x? What's that equal to? Well, we're going to have the cube root of negative x. Now this doesn't simplify at all. By evaluating this function, there's no evaluation that could be done here. This is, this is what it is. Nothing could be done with this. So, with that being said, since this doesn't simplify any further, if we compare this to the original function, it's pretty obvious that they're not the same. So this is not the same as the cube root of x, right? Obviously they're not the same. And that means that the function at x is not equal to the function at negative x, so it's not even. So let's test for odd, whether f of x is odd or not. And in order to do that, you look at f at negative x equals negative 1 times f of x. So we already know what f at negative x is. That is right here, the cube root of negative x. Okay. Well, I want to see if that's equal to negative 1 times the original function f of x, which is the cube root of x. So are these the same? So this is negative the cube root of x. Is that equal to the cube root of negative x? In other words, can I pull this negative out? And the answer is yes, I can. So even though over here I said nothing simplifies, the reason why I said that is because when compared to the original function, it's not going to do anything. It's not going to make a difference anyway. But this is actually, you could do this. You could do that. You could take the cube root of a negative number, just like you could take the cube root of a positive number and have a negative sitting on front of it. The result of this will be negative. So yes, this is true. I can take the cube root of a negative number and get a negative number. That is true. So yes, that's fine. So that means this function is odd. So since the function is odd, what we know about odd and even function is if I have an odd function, that means I could say it's also symmetric to the origin. That means the original function is symmetric to the origin. So that means whenever I graph it, I could just invert it against the x-axis and the y-axis. Basically, I could fold it over both axes at the same time. Okay, we're combining steps 1 and 2 together to get an idea of what the graph of f of x will look like. So in number 2, so this piece of information that's important. That's going to help us sketch f of x. But in number 2 will also help us. So let's look for intercepts. So the x-intercept means y equals 0. So set this equal to 0. And the cube root of x equals 0, well, that means you could just take, if I want to get rid of the cube root, I could just cube both sides to get x. So when I do that, I get x equals 0 cubed is just 0. Which means the x-intercept is 0, 0. And the y-intercept, that's when x equals 0, that's even easier. That means you're just plugging in 0 into the function. So f at 0 is the cube root of 0, and the cube root of 0 is just 0, which is the same point. 0, 0, which is the origin. So I only have one kind of intercept, the origin. That's all I have. I know the graph is odd, which is symmetric to the origin, but other than that, I really don't know what the graph looks like. So, you know, this is why you need to be familiar with the basic understanding of common types of functions, so that you can use these techniques of identifying intercepts and symmetry to, you know, get more sophisticated versions of those graphs. Okay? So, if I were to get an idea of what this graph looks like, if I didn't know what the cube root of x looks like, how would I know? Well, in order to get a basic understanding, note, in order to get an idea of a structure of a typical function, just plot several positive points. So, you know, go back to the basics. Let's plot some x values, some positive x values. So 1, 2, 3. And then once I get this idea, I could use the symmetry and the origin idea, or I could combine these two things together to build, or I'm trying to think of a better word. Not build, but like to accelerate the process, if that makes sense. Instead of plotting points to get the whole function, which is tedious, I could just plot a few points to get the basic idea and then use this to accelerate it. So when I plug 1 into my function, so that's just a cube root of 1, which is 1. So the order 0.11 is on there. Okay, well that's easy enough. It's right there. When I take the cube root of 2, well, I would normally just leave it like this, but this is an approximate number, so let me type it in my calculator. So cube root of 2 gives me approximately 1.26 if you type it in your calculator. So that's the ordered pair 2, 1.26 roughly. So, ooh, that was an accident. 1.26 is, so, you know, I'm just approximating here. But the idea is you're just getting an idea of what this graph kind of looks like, and then you're using symmetry and the origin to accelerate this process. And if I do the cube root of 3, I get, so math, cube root of 3, I get 1.44, which is the order pair 3, 1.44, which is not much higher up from the y value of number 2. Okay, so now, you know, I could keep, you know, I could be plotting points that are negative x over here, but I don't need to do that. I could use the symmetry, and I could use the any intercepts I found to, you know, speed up the process. So just by plotting these points, I could see my graph is kind of doing a little curve here, which is the basic structure of the cube root of x. Okay. Now I know that symmetry to the origin means I'm going to reflect this graph against the y-axis and the x-axis simultaneously. So just take that graph, and fold it over the y-axis, and that gives me this. And then take that graph and fold it over, I'll just dash the x-axis on here. Then you take that and you fold it over the x-axis, which roughly looks like, trying to get a crease here, which looks like that, roughly. If my post-it will cooperate with me, but that's what symmetry to the origin looks like. So take that and just graph it here. So there's the rest of my function, f of x equals the cube root of x. And that's just by using symmetry. That's it. So if you didn't know what this, these basic graphs looked like, this process of graphing a random function can get a little tedious. That's why it's important that you should know the basic ideas behind certain graphs. And that's what the rest of these notes basically touch up on. Summary of basic graphs of functions. And, they're all here, but, I give them to you in your notes pretty conveniently. But I'm going to summarize them on the back here just so I can, kind of summarize them in a little bit better, more clarification anyway. So a linear function. You should know what linear is. This is number 1. So if I have a graph, linear is, y equals mx plus b. My camera is being weird. So a linear function looks like this. It's a line. Specifically, this one is an example. This one is the line y equals x. But this is what it means for something to be linear, and you're familiar with that one. I mean, that one is pretty common. So this is a linear function. I said y equals mx plus b, but you could also use function notation. All right, f of x equals mx plus b. So another kind is this. These are in your notes, but if you have a constant function, this is when f of x equals a number. I usually call it b. So what does that graph look like? It looks like a horizontal line. Well, it is a horizontal line, it's just that my ruler, I'm making do with what I have here. So this is the line y equals b. That's a constant function. You know, you shouldn't. This is a horizontal line. You know this. These are very basic. They're things that you may or may not recall coming into this course. Other types. This one is a square function, or we call quadratic. This is when you have f of x equals ax squared plus bx plus c. All right. A square function. We call it a square function because the highest power is 2. This is also a quadratic. We're going to talk about those a little bit later. But a quadratic function has, so the most basic kind of quadratic function that we should be most familiar with is y equals x squared. That's the most basic one, that's just a parabola. And that goes through the origin. It looks like a U like this. You could see that it has symmetry to the y-axis, which means it's an even function, right? But that's the basic structure of y equals x squared, and you should be able to recall that pretty easily. This one's a cubic function. And that's when f of x equals ax cubed, the highest power would be to the third power obviously, plus bx squared plus cx plus d. And this is a cubic function. Now, this is the most general form of x squared. Now, later on in the course, you're going to see variations of this graph, which is called a parabola. You're going to see different variations of this, like not just x squared, but you'll see all kinds of different things. But they're all going to have this inherent shape in common. They're going to have this U shape to them. They just might be moved to the left, to the right, whatever. But I'm getting ahead of myself. A basic cubic function looks like the following. So the most basic form of a cubic function is y equals x cubed. And you may or may not recall this, but you should be able to remember this pretty easily in this course and going forward. It starts off pretty small, but it gets big really quickly because this is a power function, but it does this initially on the right side. But then because this is actually an odd function and has symmetry to the origin, it's going to do this as well. So it's going to reflect about the y-axis and then the x-axis. And you should be able to recognize these patterns pretty quickly. There are a few more. I think there's a few more. Number 5, let me come back up here. Number 5. So the square root function. Which means f of x equals the square root of x. So when you're graphing, the most basic form of this, y equals the square root of x, well, we may have looked at this already, but it starts off with big values, but then as x gets bigger, y gets smaller. So as x gets bigger, y gets smaller and smaller and smaller, and it keeps getting up, but it keeps going up very, very slowly. It's increasing, but very slowly. All right. So this is the square root of x. Now, typically when we deal with square root, we write plus or minus. So you may see variations of this. You might see this, and the minus would just be down here. But this is the square root function. And, well, we also see the cube root function pretty often. We just did it. F of x equals the cube root of x. So y equals the cube root of x. So we just looked at it on the previous page. We knew it was an odd function. It looks like this, right? It starts off small, but then it, as x gets bigger, or the values of y, they get smaller. Well, I mean, the values of y get bigger, but they get bigger very slowly, is what I should say. So, as you're starting off here, it's going like this. It actually doesn't look much different initially than the square root function. It almost looks the same, but there's one difference. This is an odd function. The square root function is neither even nor odd, but the cube root function is odd. So I could take this and reflect it about both axes and get this as well. So that's the cube root function that we already did on the first page of the notes. It doesn't look much different than the square root. Then there's two others here. One of them is called the reciprocal function. Which looks like f of x equals 1 over x. Reciprocal function, is also another name for it. It's called a rational function. And we're going to look at rational functions in detail in Chapter 5. But the goal of this section is to be familiar with the basic structure of these, the basic structure of these functions. And any variations of them will involve techniques that we're going to look at in the next section. But the reciprocal function basically looks like the following. You have a little curvy U like this in the first quadrant. So it borders the y-axis and it borders the x-axis, but never crosses them. And then this function is actually an odd function, so you could take it, reflect it about the y and x-axis, and get the other side over here. Basically what's going on here is these graphs, they border the axes, but they never cross them. Okay, they hug them, but they don't ever cross them. And that concept we'll look at later. That's actually called an asymptote, but we'll discuss that later in Chapter 5. And the last one we're going to look at is absolute value. Which has a structure of f of x equals absolute value of x. And you should know what that looks like. looked at that a number of ways, but the absolute value of x has a V shape to it at the origin. That's the absolute value of x. So these 8 functions are something you should be familiar with when it comes to making general sketches of equations, depending on what you start with. All right, it depends on what you have. You're going to take this, like if you have a square function, if you have a quadratic function or a cubic function, you're going to take this and use it to get whatever it is you have specifically. And you'll see what I mean in future sections when I look at them, but that's the basic idea, really. Okay? Okay. So, you know, linear, constant, this is a parabola, that's for quadratic or square, cubic, square root, cube root, reciprocal, absolute value. They're the big ones you should be familiar with in their structures. Okay. And we're going to use those graphs I just made, those basic variations, in the next section more specifically. But the last topic in this section is piecewise functions. And in my experience, when looking at piecewise functions, students tend to get confused with this. Actually, this is an error. Ignore that. That's an error. F of x, it should just be this. F of x is equal to this. So what is a piecewise function? Basically, a piecewise function is a function defined differently by the values of its domain. So it depends on the values of the domain. So the absolute value function is an example of such a piecewise function. As we know, absolute value can be a positive number or it could be a negative number, depending on the value of x. We don't usually write the absolute value function like this, but it can be written like this. If you take the absolute value of a positive number, right, if x is greater than or equal to 0, then your result is positive. If you take the absolute value of a negative number, so if x is, you know, the result of that could be negative, right? If x is positive or negative, that'll give you the absolute value of x, basically, as well. That's what absolute value function is saying. The input could be positive or negative, x or negative x, and the result will be positive. So basically all I'm saying is a piecewise function is broken up into pieces. Go figure. And the pieces it's broken up to depend on the values of x. So note, the values of x determine the overall structure of the graph of a piecewise function. They do. So so basically, if x is a specific value, it could go to one part of the function or another part, depending on what x is. That's really it. So I could say another thing here. F of x can equal one of several equations depending on the value of x. That's what f of x, that's the description of a piecewise function in words. Okay? So when it comes to finding the domain of f of x, you're just looking at all the values. All possible values of x. So look at, so f of x equals x plus 2 if x is a caught between -4 and -2, including -4. So really I'm looking at all the different values of x and I'm combining them together into one domain. So I have the first inequality, I have the second equality, and I have the third equality. And if I sketch all three of these values on a number line, I'll get the domain of f of x. I'm just basically combining those three together. So let me put them on a number line. And that's just a combination of all those values. So I have so my breakpoints, the values that break up on each piece, are -4 and 2. So let me include them on my number line. So let me sketch this one first. So -4, x is greater than -4 but less than 2. So I'm including -4, so that means I'm going to have a solid dot in -4, right? And x is going to be greater than -4 or less than 2, so that'll be everything between -4 and 2. Now this inequality means it's going to be an open dot at 2. Okay, so that's this one. Now what's this one? X is 2. Okay, so that's also part of my domain. So now I'm going to fill in the dot. I'm just including all three of them. And now, what is this one? This means x is greater than 2, so that's everything to the right of 2 forever and ever. So that's the third one. So if I were to write all three of these inequalities and equalities as one equality, I'll get my domain of the whole function. So what's the domain of f of x, my piecewise function? It's this sketch, which is from -4 up to, and it goes all the way out to infinity. Infinity is always open, and -4 was included, so it's a bracket there. And that's it. So my domain altogether is from -4 to infinity of my piecewise function. Okay. Now if I want to locate any, well, that should be locate. Locate any intercepts. So my x-intercept is when y equals 0. So that means I'm going to set my function equal to 0. Right? Okay. Now let me ask you this. How do I know which function I'm going to set equal to 0? All right, that's what this means. I want to find x when f of x equals 0. That's what the x-intercept is. Okay, well, what you could do is you could set, I mean, I don't know which one I'm going to set it to, so I'm going to set it to all three of them and see and just go with it. I'm going to set x plus 2 equal to 0. I'm going to set 2 equal to 0. And I'm going to set x divided by 3 equal to 0. And I'm going to look at each one of them. I know this looks a little confusing compared to what you usually do, but I'm just following the steps. I'm trying to find the x-intercept. I'm just trying to find x when the function equals 0. Well, my function is 3 different things. So I'm going to set all 3 different things equal to 0. Now let's look at each one. All right, x plus 2 equals 0. Well, that means x equals negative 2. Now, let's look at this. This looks good. When x is equal to negative 2, my function equals 0. Good. Now, is x equaling negative 2? Is that inside this interval? Yes, it is. Negative 2 is in this interval. So this is good. So that is an x-intercept. That is an x-intercept. That's the x-intercept negative 2, 0. So that is one of my x-intercepts for my function f of x. Now let's look at the second one. 2 equals 0. Does that make any sense? No. That makes no sense. So I don't care about that. Let's look at this one. How do I solve this for x? Well, I can multiply both sides by 3 and get x squared equals 0. Take the square root and get x equals 0. Okay, well that looks good. However, there's one little problem with that. X equals 0, is that in the interval for when f of x equals x squared divided by 3? In other words, is 0 greater than 2? It is not. It's not. So this one's no good. So I don't care about that one. The only one I do care about is this one. Okay, so basically the only x-intercept I have is negative 2, 0. And you know, just take each piece one step at a time. Now when it comes to finding the y-intercept, that's when x equals 0. So that means you want to find y or you want to find the value of f at 0. You just plug 0 into your function. So that's easy enough. So f at 0 equals what? Well, when x equals 0, which one do I go to? So 0 is in the interval from negative 4 to 2. So that means I'm going to go to this one right here, x plus 2, or more specifically, 0 plus 2. Which gives you 2. So my y-intercept is 0, 2. Okay, so those are my intercepts. My intercepts are negative 2, 0, and 0, 2. Now I want to take those. Now my next question is to graph the function below. So I'm going to do this as carefully as I possibly can. So there's my y-axis. There's my x-axis. So I want to graph them based upon their values of x. Now, when it comes to graphing a piecewise function, it can be a little, different than what you're used to. But it's really not that bad. All you have to remember is that f of x can equal one of several equations depending on the values of x. Okay? So I know that my first function equals x plus 2 when x is in this interval. So let me just kind of write that down here just for reference. That equals that on the interval from -4 to 2. My function equals the value 2 when x equals 2. And my function equals x squared over 3 when x is greater than 2. Okay. So let me devise an increment system here just so we're very consistent. What I'll do is I'll skip every other one as 1 unit. So this one right here, that's 1 unit. The next one, that's going to be 2. So that right there is the value x equals 2. Now I know that this breaks up on the value of 2, right? This interval breaks at 2 on the right, and this breaks at 2, and this breaks at 2. So I want to clearly visualize x equals 2 because it's at that vertical line. It's at this vertical line where the graph could look different. This is not part of the graph. This is just here to distinguish what the right side of it looks like and the left side of that looks like. All right. The leftmost value of x is -4. So let me go to -4. So that's -1. That's -2. That's -3, and that right there is -4. Let me make some ticks on the y-axis here. So that's -1, that's -2. All right, here's 1, and there is 2. Okay. So all I did so far was just devise an increment system, so I'm consistent. I identified x equals 2 because that's where these intervals break at, 2, 2, and 2. This is not part of the graph. This is just there to help us make the graph a little easier to sketch. But what I want to do now is I want to start plotting pieces of my graph. So in question number 2 here, I asked you to locate any intercepts. So I already found one of the x-intercept is -2, 0. So I could plot these points because that's part of my graph of f of x. I could plot those. So let's do that. So -2, 0 is on my graph. I'll graph it in blue. So -2, 0 is right here. That's the single x-intercept. The y-intercept I have is 0, 0, 2, which is right there. Okay. So, as you can see, from -4 to 2, I have a straight line. I have a linear equation, x plus 2. And you can kind of see that from the points right here. You can see that they form a straight line. And you know what a linear equation looks like. It looks like, you know, this has a slope of 1 and a y-intercept of 2, which obviously is included right there. So I know in between here I have a line. I have a straight line. I know in between those 2 points I have a, you know, they connect to form a line. I just got to be careful about what's to the left and what's to the right of these points. Now, I know that f of x equals x plus 2. That's part of the graph from -4 to 2. Well, at this point I'm at x equals -2. So, but my interval for this part is from -4 to 2. So I know I could take this and I could go out to -4 and down to 2, or -2. So this point is -4 for x, this point is -2 for y. Okay, so the leftmost value here is -4 for x. So when I plug -4 in here, I get -4 plus 2, which is -2. So that point is on this line. I'm just going to include it on here to make my graph a little easier to make. That's the point -4, comma, -2. And I got that by plugging -4 into f of x equals x plus 2. Because it goes from -4 to 2, right? So at -4, y is -2. That's that point. So this is just a continuation of the line. Okay. Now I do not extend this out with, do not do this. I do not make dashed lines like this. I do not. Why don't I do that? Because my line x plus 2 only goes from -4 to 2. If I were to do this, that would, you're suggesting that x goes out to -infinity, but it doesn't. That's not how my piecewise function is defined. So just be careful about that. Okay. All right. So that right there, so far, is part of my line, but the largest value in this interval is 2. Well, this is the x value 0, so I could go a little bit further out here. So when I plug 2 in here, I get 4. Okay, so the point 2, 4 is part of this line. So 2, 4, so 1, 2, 3, 4. So 2, 4 is right there. Now, I want you to be careful here. Because at the point 2, I want you to look at the value of 2. Is 2 included in this interval? It is not. 2 is not included in that interval. So that means this dot right here isn't actually on this line. It's actually an open dot, which means it's not included on that line. So I could sketch the line in between, but once I get to 2, I'm not on this line anymore. What happens when x is actually equal to 2? My function is actually equal to 2. So the dot that is filled in is the order pair 2, comma 2, which is the second part of the piecewise function, which is right here. 2, comma 2 is part of the graph. So once I get to 2, I jump off this line and I come down here to 2, 2. This is an open dot. This right here is closed. Okay? I know this looks confusing, especially if this is the first time you've seen piecewise functions, but that's how you do graph them. This right here is my graph thus far. Alright, my graph, I'm on the line x plus 2 until I get to 2, then I jump down here. That's all I'm saying. From -4 to 2, I'm on the line x plus 2. But then once I get to 2, I jump down to the point 2 for y. And then once I get greater than 2, I jump onto the value x squared over 3. So what does that look like? Well, when I plug 2 in here, I get what? I get 4 over 3. So 2, 4/3. Well, I'm just getting an idea of where the start of this graph will be. So 2, 4/3. Well, this is 2. 4/3 is just above 1. So 1 is right there. So it's roughly right about here. And that's open because that value of 2 is not included on this function. That's why the open parentheses here is at 2. And this is as we already know, this is a this is a square function, x squared, but it doesn't look exactly like x squared. It's divided by 3. That's okay. It still has this basic shape to it. Alright, the square function still has this basic shape to it. It just looks a little different because it's divided by 3. But if you want to extrapolate from there, that's fine. X squared divided by 3, it's elongated a little bit, and we're going to look at what that means in the next section. But as long as you capture the structure, as long as you capture this structure, that will be sufficient. So from here out to infinity, my graph is going to look like this. Roughly. And that right there is a graph from everything from here, that's a solid dot, to here. So this right here is a graph of this piecewise function. I know it looks a little sloppy, but that's what it is. And it's important to note that you're just graphing each piece based upon the values of x, which make the function equal to whatever it is. When from -4 to 2, I'm on that line. But then once I get to 2, I jump to y equals 2, which is right here. So this open dot jumps to this filled in dot. And then I jump to this next open dot from 2 out, which is the square function x squared over 3, which looks like this. And that's it. That right there is my graph of my piecewise function. And that's how you graph any piecewise function in general. Just look at the values of x and look how they go from one to the next for each piece of the piecewise function. The only time you make arrows like this is if you know you're going out to infinity or negative infinity based upon how your piecewise function is defined. That's why I emphasized do not do this unless it tells you to do that. Like if this were just strictly x is less than 2, if it were that, then yes, you would do that. But that's not what I have. Okay, so you know, the thing you should take away from this section is graphing, you know, having a basic idea of those various functions I showed you, and graphing a piecewise function or two, okay? Knowing how to do that. Those are the important concepts you should take away from 3.4. So that's the end of this video.